Okay. Yeah, so like Jesse and Tom said, my name is Max Watkins. I'm a staff scientist in charge of the SAXS user program, and I'm going to tell you about what our current capabilities are, what's changed, what's new, a little bit of what's the same, but mostly what's new. And hopefully some of you will be excited about some of this. So just very briefly, an overview of our SAXS program. At BioCAT, we support both equilibrium and time-resolved experiments. And so in our equilibrium mode, we do a lot of separation coupled experiments, so size exclusion, chromatography coupled. We also support ion exchange, and as I'll talk about later, a new capability, asymmetric field flow field fractionation, or AF4 coupled SAXS, which is a really exciting new technique. We offer a lot of inline characterization, some multi-angle light scattering, DLS, RI, full spectrum UV, full range of temperature control. And finally, we also offer batch mode as well. If you don't need the separation, you can do very low volume batch mode, which is a new capability that I will talk about. In addition to equilibrium modes, we run time-resolved SAXS experiments, and this is one of BioCAT's unique capabilities. We run continuous flow mixing, time-resolved SAXS, with a couple of different mixers that allow us to access time ranges from 45 microseconds all the way out to about a second and a half, depending on the setup that you use. So I'll talk about each of these systems sort of a little bit more in depth over the course of the talk. And like Jesse said, because these are sort of time limited, I'd say maybe a quick question or two, but mostly save questions, I think, for the Q&A later if you have them. So I'm going to start by talking about what's going forward. We expect to sort of be our workhorse experiment, which is our chromatography coupled SAXS instrument. So prior to the APS-U, we ran chromatography modes off of a couple of different instruments, size exclusion chromatography without the inline characterization, mols, whatever. We generally ran off of an ActivePure. If you had mols, we run off of one of two sort of Agilent HPLC stacks with the wide instruments plumbed into them. So those instruments have all been retired or repurposed, and all of our chromatography coupled experiments going forward, we expect to be run on this new sort of semi-custom instrument, which you can see on the right here. So this thing is basically just a couple of Agilent HPLC parts. So it's two pumps and an autosampler plumbed with a series of valves that allow for simultaneous column equilibration and running at the same time. And so you can run an experiment with one column, you can equilibrate your other column, and then with a single click of a button, you can switch flow paths and switch to the other condition. So you can, in theory, because we have buffer switching valves as well, run up to 10 buffers on two columns. Without interfacing with the system at all from a physical perspective. The entire thing is housed in this giant metal incubator, which allows us for really nice full system temperature control from about 4 to 40 degrees Celsius, which is mostly limited by the column hardware. And finally, in addition, Jesse spent a lot of time over the down working with Agilent's API to integrate control of this system into our BioCAT software, which is our Python GUI-based Beamline control software that lets you control experimental parameters like exposure and stuff like that. So it's really, from a user perspective, we're trying to streamline the interface, so users have to interact with sort of less windows while they're collecting data. And from our perspective, it allows us to automate more stuff. And so going forward, not this run, but in the future, we expect to be able to offer sort of unattended overnight running as well down the road. And so this is just a picture of what the setup looks like. It's in this like 600-pound giant incubator. The pumps, the valves, everything is all in there, and you can set the temperature to whatever you want. And so just in case your people are curious, if you've ever been to the Beamline before and you come back for a SAXS experiment, it'll look a lot different than it used to. There's a lot more stuff sort of on the table. But basically the idea is we have these detectors already on the table. Just roll this giant card up to the Beamline, plumb it in, and then you can load your samples and hit go. And you'll notice here at the picture on the right, the co-flow fluidics, which I'll talk about a little bit later, are contained in a similar incubator. And this is part of our overall effort to improve the temperature control of all the systems at the Beamline. So just a very quick look at what data is actually going to look like. So these are a bunch of SEC traces. So it's integrated intensity. This is actual SAXS data. If you're familiar with SEC SAXS data, this will look very familiar. This is showing BSA injections on sort of the standard setup. This colorblind blue purple curve at the top is what we consider sort of a normal running mode, relatively high volume injection with a SuperDex 200 10300 column. It's one of the GE, or formerly Sativia, columns, or all the way around. And so, we're getting, I think, really pretty good performance out of this system. We'd spent a lot of effort trying to replumb stuff, optimize some of the resolution on it. And then we're getting almost baseline separation between the BSA monomer and dimer, even with the mols in line. If you take the mols out of line, you get a little bit less band broadening, you get even better resolution. And if you really, really want to push the resolution, you can use low volume injections. This bottom one here is about 50 microliters on a 10300 column, and you can still get perfectly usable data from that amount of sample. And so we're really excited with how this system is performing. We think it's doing really great. And just to very quickly look at the fact that we are actually doing a little bit better in terms of band broadening at the SAXS sample cell compared to the old SECMOL system. This is a comparison of a BSA data set from a couple of years ago, and we are doing a little bit better. So we're excited about the performance of this thing and the ability to run a bunch of stuff and automate things, and hopefully you all will get good use out of it. So I'm going to talk about sort of the other new, I guess other is wrong, but one of the new capabilities that we're really excited to roll out, which is the ability to put a different separation technique in line with SAXS. This is asymmetric full field fractionation, or AF4. So this is relying on diffusion and parabolic flow through a narrow channel, basically to separate molecules by size. For the sake of time, I'm not really going to get into the details here. If you're curious more about how this works, I'd encourage you to follow this link at the bottom and read about it on Wyatt's page, or you can stick around and ask about it in the Q&A later, and we're happy to talk about it more. But the important thing to note is that in this technique, there's no stationary phase, so the molecules are not experiencing any shear. And so this lends itself to a couple of very potentially interesting systems that are not maybe amenable to size exclusion chromatography due to the fact that there is a stationary phase in the column. In particular interest, people have been using this technique increasingly for analysis of lipid nanoparticles. Those really tend to fall apart on columns. They're not really great for SEC, but they work really, really well for AF4. We also anticipate that things that have a lot of problematic column interactions, or maybe some weak macromolecular complexes that fall apart due to column shear, might also be amenable for this sort of thing. So we have a range of channels and spacers and membranes that you could use. This is something that's going to be routinely available to users. I should note that if you're interested in using this technique, it's not necessarily as plug and play as SEC. There's a lot of parameters that you might have to play with your method to really tune the separation. It's a very powerful technique. The separation can be tuned to a huge range of systems. But there may be some back and forth that's required. If you don't have access to a system, we may have to help you, optimize some stuff online before your beam time. But that being said, don't be afraid of it. If you're interested in using this, absolutely get in touch, and we'll work with you to try to optimize your system and get it ready for beam time. And so, the way this works at the Beamline, we took one of our old SECMOL stacks, one of the Agilent stacks, and plopped this wide eclipse on it, and we roll the cart up just to the Beamline the same way we do the chromatography carts. We're not, of course, running through the mols and the RI detector that are already on there. We're running through the ones on that stack. But same idea, we just swap the carts out, plumb it in, and then it runs very much in the same way as the chromatography setups do. So just to show that we can actually get data from it, we were able to test this with X-rays during our commissioning. It was showing this is actually a mols trace, but if you notice, this is also BSA. It's reverse phase with respect to SEC, so smaller stuff is actually coming out first. We're still doing a little bit of work to optimize the actual resolution that we get at the sample cell, playing with dilution control, flow rates, all of that. There's a lot of stuff. But we can already get good quality data. This is a separated BSA monomer from a real SAXS data set with sort of a normal-ish injection. So we can already get good data from it. It's user available, and we are happy to work with you if you have experiments that you want to try. So now I'm going to switch gears from the separation couple buds and talk a little bit about batch. So prior to APS-U, so batch, no separation, just sort of direct injection into the cell, old school SAXS. We basically we injected under a valve, and then it sort of continuously flowed through the cell, which was fine. You were able to get good data, especially with the co-flow cell, but it was pretty low throughput, a lot of user sort of interaction with the system, a lot of error, easy to inject bubbles, not automatable, not very fast. So we completely overhauled the way we do batch mode. And the strategy we're taking now is basically direct needle injection from, you can do 96 or 384 well plate. And so this enables us to have a level of automation that we can roll out, as well as full temperature control. The plate's cooled, the cell's cooled. And really excitingly, it allows us to run with much, much lower volumes than we used to. So during our commissioning, we were able to get what we consider to be good data from sample volumes as low as about 10 microliters. So when you run this experiment, it is, you're injecting directly from the needle. It's flowing continuously, so your data looks a little bit like a SAXS trace. But what you really want to look for is, if you can see the top of this peak, is sort of a range of constant concentration. And as long as you get that, you can just pull the profiles from that, average them, and that's your data at the concentration in which you loaded. And like I said, the volume that we were able to achieve is about 10 microliters to get sort of that result, which we're really happy with. I should note you can do larger volumes than that, of course. And you can do lower volumes. We were able to get a profile. This is just a profile from the same one. We were able to get a profile from a volume as low as about 4 microliters if you don't quite care about the constant concentration. So this is, I think, a really powerful new capability that we have. It's not super, super high throughput like you might see somewhere at like ALS. But it's much higher throughput than we could do before, much, much lower volume, and you can automate a full 96-well plate as well if you want to do that. So what does this look like? The very short version is basically this plate here. It's just on a two-axis linear stage. You take the needle, it's on a vertical stage, you move the needle up, you move the plate in, draw from the plate, move the plate out, move the needle back into the SAXS sample cell, inject, and collect your data. And that's sort of how this system works. Okay, so just very briefly, some other sort of things we've upgraded about our equilibrium setup. We did a little bit of work improving our COFO cell design. So for those of you who don't know, all of our equilibrium experiments, the sample cell is a COFO cell, which basically involves running a sheath of buffer around the main sample stream. And this is a really, really nice strategy for protecting the sample, protein, RNA, whatever, from the walls of the capillary. It isolates it from the walls of the capillary, and that does a really good job of protecting it against accumulating radiation damage. And so we've been running with this cell since, 2018, I think. We took the down period as an opportunity to sort of revamp the design and commission a new cell. The really big thing that we've improved is the temperature control and feedback. So instead of sort of contact cooling, it's now got integrated recirculating coolant and a built-in thermocouple, so we can have temperature feedback. And this is part of our larger effort to have much higher fidelity temperature control over the entire system. So this cell's been commissioned. It's going to be in use next run. Like I think I mentioned previously, we put a bunch of fluidics in an incubator, so we have temperature control over those as well. Okay, now I'm going to switch gears and talk a little bit about time resolve SAXS. So this is, as I mentioned before, one of BioCAT's unique capabilities is time resolve is continuous flow mixing time resolve SAXS. So if you're not familiar with it, it's exactly what it sounds like. It's you take your sample and you mix something in, and then you take a series of time points after mixing, and that's how you get your time series. And our capabilities are basically now they're the same as they were before the APS upgrade. And so we run with 2 different mixers. We have a chaotic flow mixer that we use for very fast time points. It's high sample consumption. Sometimes you might need like a couple mils of sample to get your data set. But you can get really, really fast time points, at least for mixing, down to about 50, 45 microseconds, and then all the way out to about 75 milliseconds. And then for slower time ranges, we have this laminar flow mixer design that allows us to get from a millisecond to about a second and a half. And there's a lot of overlap between these mixers if you want to use both of them. There are a couple of upgrades to the system that we do have in the pipeline, where this year we're hoping to put the cell in vacuum, which we expect to significantly improve signal to noise. And so you can less sample to get the same amount of same quality data. And especially with the new optics, which Jesse talked about in the last talk, we think that that's going to help beam size significantly, enable us to get to lower Q, faster minimum times, especially for the chaotic mixer. So in about a year and a half, this system, I think, will perform even better. That being said, as it is from a user perspective, basically plug and play now. We do all the setup, we do all the motors, the timings, the pumps, and everything. So you can just come with your sample, inject it, and get a time series. Even if you have no previous experience with time resolve SAXS, it is a general user available system. So the last things I'll show, because I'm almost out of time, are what this actually looks like at the Beamline. So this is the chaotic flow mixer. So for the really fast time points, it's this 3-inlet S-bend design. We run it very fast flow rates, 4, 6, 8 mils per minute. So we're running it off of a couple of standalone HPLC pumps. And the way it works is you basically inject your sample into a valve with a loop, start running the HPLC pumps, collect your time series. You're essentially scanning along the mixer and getting a whole time series. And then you can just do repeated injections and build up your signal until you are happy with the experiment. A laminar flow mixer works in much the same way, except you're running off of much slower flow rates, much lower sample consumption, SEC amounts of sample. You're running off of syringe pumps in this case, but the idea is essentially exactly the same. And so with that, I'm gonna end. I'm gonna leave with sort of this cheat sheet of equilibrium capabilities, which can also be found on our website if you're interested. And with that, I guess I could take maybe one or two quick questions, or if not, for the sake of time, we'll move on.